Hello physics students. Today we're going to do another example where we use Newton's laws to analyze the motion of an object. And today we're going to look at objects that are passively pulled along. But before I go into that example, what I want to do first is review again Newton's laws, because that's what we're going to use to analyze the situation. The first one is Newton's first law: objects at rest stay at rest unless you act upon them. And objects in motion stay in motion unless you act upon them. And then the second law is the one we express as an equation, A equals F net over m. So that's actually two ideas in one equation. More force makes more acceleration, and more mass in the bottom of the equation makes less acceleration. And then the third law is that whenever any two objects touch, like if object A strikes object B, B strikes it right back with the same number of newtons. And it doesn't matter about size, strength, or damage. The forces on either are always the same. So those are the laws. And we already studied in the last video objects that accelerate due to their own efforts. Like a runner has muscles and legs and pushes the earth back, and friction then accelerates the runner forward, or when they slow down, they push the earth forward, and then earth pushes backwards with friction, and so that causes the acceleration and deceleration. But today, we're looking at things that have no motors, no muscles, like boxes or rocks or whatever you want to call it, and they're pulled by something outside that object, a second object, because obviously they can't create their own acceleration. So passively pulled along. That's what we're going to analyze today. So we're just going to study this motion through a couple examples. So title for today, objects passively accelerated. The first example, we've got a worker pulling a 40-kilogram wood box over a wood floor with a horizontal force of 150 newtons. And our goal is to determine the acceleration. So here's just a little diagram of what's happening. You've got this box pulling horizontally. You never have to draw this. What you really have to draw in Newton's laws problems is the force diagram. Now this force diagram is incomplete because I wanted to make a little point for you. First of all, the earth pulls down with mass times 9.8, whatever number of newtons. Not important to put the number of newtons here, but more important to label it that it is the force of gravity. That's what you get credit for. The box, of course, doesn't fall because it's resting on the wood floor, so the wood floor doesn't let the box break through it because it supplies a normal force to keep that box from breaking through. In this case, it'll be equal to the force of gravity. Now, in yesterday's example, when it was a person running in a track meet at the beginning, they pushed the earth back, and then the earth pushed forward with and that was force of friction. Okay, so that created a forward acceleration. This time, it's not that. What happens is we've got a person who pulls on this, a worker, with a horizontal force like this. Okay. And then, because that is being dragged along the surface, then we have a force of friction that's going to go in the backwards direction. We're going to see that that force of friction is actually less than the applied forward force, meaning there's a net force in the forward direction. I also want to point out something that, in my opinion, I didn't emphasize enough in the last video. When the runner ran or the car took off and there was no tire burnout or no sneakers slipping, it was static friction because the sneaker was on the surface and then you started running. There was no slipping. The sneaker was like rooted. So that's when there's no slipping, that's static friction. But today, as this being dragged over, this is actually kinetic friction. So you could even put a little K here. It's not necessary, but that's sometimes some physics people do that to indicate it's kinetic versus static, the sliding one. Okay, so let me pause the video, put a pause in here to give you a chance to catch up if you need it. Okay, so let's now move on to the analysis over here. So the first thing that we're going to do is figure out these lengths of these arrows. Why do we need the gravity and the normal force? Because there's friction involved, so we got to calculate the friction. So the first thing, gravity, force of gravity is mg. Remember, that's on the reference table. It's right around here, okay, somewhere in the center. So you take 40 times 9.8, you get 392. That, as we could see from the diagram, has to be matched by the normal force. Otherwise, this is going to accelerate downward. So we can now use that in the friction formula, which is right here on the reference table, right? So as you can see, force of friction coefficient times normal force. And then where do we get these values? Well, this is the coefficient right here, 0.3. I figure that out, or I find that on the front cover of the reference table. So right here in this table, there is some coefficient of friction values, and what we have is wood on wood, which is right there. And then since we're dragging this box, it is not static, but it's kinetic. So it's right there. Wood on wood kinetic. When there's sliding over a surface, you use the kinetic value of 0.3 for wood on wood. So that's where this came from. And then, of course, the normal force was just equal to the gravity. 118 is that friction force in the backwards direction. So now, finally, we can use Newton's second law. A is F net over m. We see that there is indeed a net force in the forward direction. We can find its magnitude by doing this minus that. That's from Unit 1 of our physics course. Forward minus backwards, and that's what I have right here, the force applied minus the force of friction over the mass. And then what we have is the numbers. 150 was given in the problem, 118 of friction we calculated, all over the mass of 40 kilograms. Turn that out on your calculator and you get 0.8 meters per second squared, okay? So there is our first analysis using Newton's laws. But I also want to point out that we just use the forces unit here, but also the kinematics unit will come into this topic also. Sometimes you may have to graph the motion of this object as this person's accelerating it. I want to remind you, when something accelerates, the displacement graph is a parabola. D equals 1/2 AT squared, right? So that's a curve. It's showing increasing velocity as the slope increases. The velocity graph goes up because you're going faster and faster as it's accelerating. And the acceleration is straight across, constant value of 0.8 the entire time. So it's 0.8, 0.8, 0.8, 0.8 as long as these forces are maintained. So that is our first example. Let me put a pause in here to give you a chance to catch up. Now let's go on to a second example. Okay. Okay, so now, once this box gets up to speed, and now the worker's now dragging it at a steady 2 meters per second, we want to determine how much force it takes to pull it at that steady rate of 2 meters per second. So let me just say that this example is very popular on the Regents. They like things with Newton's laws moving at a constant velocity. So this is, I would say, something to be emphasized. So the force diagram in this instance, no, maybe I'll move it over just a little bit. We have force of gravity and normal force still, just as before. And they have the same magnitudes of 392 because nothing has changed in terms of the mass of the box. And as we're dragging along, friction is 118 in the backwards direction. That doesn't change. But how do we figure out this applied force? Well, here's what we have to decipher. Constant velocity. That means something from our kinematics unit. If you're going at 2 meters per second, 2 meters per second, 2 meters per second, 2 meters per second, and then you're never changing, there's no delta V over t. We have 2 minus 2 over time, or 0 over time. In other words, this implies the acceleration is 0. What does that imply? Well, if acceleration is 0, that implies F net is 0. So those words, constant velocity, key to a lot of Regents problems, to realize net force is 0 and to realize that that means forces balance in every direction. So to balance that, to create a net force of 0, we need the same amount of forward force. So we can say that the F applied by this worker has to be equal to the friction force. Key idea. Okay, now, a lot of people who don't understand physics well, I've said this before in the first video on Newton's second law, they will look and say 118 forward, 118 backwards, oh, the box isn't moving. And you know what? That is possible. It's possible the box is at rest and you're pulling 118, 118 and it stays there. But physics people need to know, well, wait a minute, it means acceleration is 0, so there's another possibility. That it's going at a steady, 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 steady pace. And then that's also acceleration 0, balanced forces. Okay? Once again, it's possible that you have to apply kinematics again. So the graphs of a motion for balanced forces would be, balanced forces means F net is 0, acceleration 0 means constant velocity, linear. That means that the box every second goes 2 more meters. Every second goes 2 more meters. Okay, so it's a constant, steady rise. You also need to know that the velocity graph is just straight across, as opposed to over here when it's accelerating, it's either sloping up or sloping down. Here it's constant. And you need to know that the acceleration graph, rather than a horizontal line like we see over there, it's a horizontal line again, but this time horizontal line of 0. And it's sometimes tricky to see that, so I'll just write A equals 0 underneath. So there's our second example. Let me create a pause in case you need some time to catch up. Okay, I'm going to do one more example. Okay? But this example, it's going to be on the difficult side. Much more complicated. But the good news is it almost never shows up on the Regents. In fact, I'm tempted to stop the video here and say, okay, we're done for today, but I'm just going to throw this in here just in case it comes up so I could say to myself, well, at least I mentioned it, okay? So here is the third example. Oops. Okay, so this time, instead of the worker pulling on this box straight across like this, they don't pull straight across. No, no. They pull maybe with a rope tied to the box, and they're pulling up on the rope like this. Okay. And that's kind of likely if you're thinking about a box on the floor. Well, I don't have a rope, but maybe this is a rope. And I'm pulling on the box like this because I don't want to bend down, so I use the rope like this, right? So that's possible with boxes and workers. So also I want to point out that sometimes when you have a rope pulling, they don't use the symbol F. Sometimes the symbol T is used, and T is just another force, but it stands for tension, rope tension. So if you see that, don't get confused, okay? But the analysis, here it is. I'm going to draw the force diagram nice and big because, as I said, this is more complicated. So we don't want to clutter everything up. So we got gravity still down. And that's still 392, you know, because it's still the same mass box. The Earth doesn't care which way you're pulling. It's always going to pull itself down with the same amount. But this time what's happening is the worker's going up like this. And force here equals 200 newtons up at an angle like this. What does that change? What happens when you pull in a direction like that is that basically that force is now doing two things at once. There's a horizontal part to it, which is what we normally label Fx in the horizontal direction. And the rope is also pulling upward, and that we usually label F in the y direction. So what that does is it actually changes the normal force. Let me pick a different number. Let's suppose this is 300 newtons or 300 pounds, okay, because people are more comfortable with pounds. So you got a 300-pound person standing on the scale. What happens if I go up behind them and the scale reads 300? I go up behind them and I start pulling on their belt and I pull up with 100 newtons. What's going to happen to the scale reading? Not going to stay at 300, right? It's going to go down because I'm lifting them off the scale. And in fact, if they're 300 and I pull 100, I'm going to take that down by 100 and the scale will read 200 instead of 300 because of my 100 lift. So that's basically telling me that by pulling up like this, the worker is reducing the normal force. So I'm going to draw it shorter than gravity this time. But if there's a normal force and you're dragging something, there's still going to be friction. But I know because I picked the numbers, it's going to still be less than that forward force. So that's the force diagram. If you need a moment to catch up, I'll put a pause here to give you that chance. Let's move on to the calculation. So, first thing I've got to do is figure out these components because I need to figure out the normal force so I could figure out the friction. So, and also the easy thing is the force of gravity. I'll just put 392 here. And we have that from example 1. I try to save work, but maybe by writing that I should have just written out the equation and resolved it. Okay, so now the horizontal component of that force, basically I'm going to be a little lazy and I'm going to just, instead of writing the cosine function out like this, and you don't have to write this, cos theta is fx, the adjacent side over the hypotenuse. Instead of doing that, I'm going to write the formula as fx equals f cos theta. So I still get credit on the Regents for having a formula. But it's just of a more convenient form than this. No algebra necessary here, just have to plug things in. So now I can say that I have 200 newtons and when I put that in on a calculator, what I get is 173 newtons. And we're going to see that that's going to be what causes the forward acceleration. I'll explain that in a minute, but I'll color code that for later, 173 newtons. I also need to figure out this y component, which is the opposite side. So I use the sine function, and once again, instead of writing sine as a fraction, I'll write it as a product here. F sine, the hypotenuse times sine gives me the opposite side, is basically what that formula is saying. And if I press that on a calculator, then what I get is 100 newtons. Okay. So that allows me to calculate the normal force now. How? Well, as I mentioned, if I'm 300 pounds, I pull up 100, then my scale reading goes 200. Same thing here. We got 392 here, and we've got an extra 100 lifting the 392. So this is less 100. In other words, I could write that in formula form, that the normal force is the gravity minus that y component that I'm lifting up. In other words, 392 minus 100 equals my normal force of 292. Okay. Now, finally, once I have normal force, I can get friction because I have this formula. Force of friction is coefficient times normal force on the back of the reference table. The front of the reference table, I have wood on wood kinetic, which is 0.3 as it was last time in the last example problem. So I could say force of friction equals UF normal, which is 0.3, front cover of the reference table, wood on wood kinetic, times the 292, and that came out to be, let's see what I get, 87.6, which, yeah, 87.6. There. All that work, and only now am I ready for A equals F net over M. But what is the net force? Well, if we go back to our force diagram, it's forward force minus backward force. And what is the forward force? Some people will be tempted, well, the worker's pulling 200, so that's going to be the forward force minus the friction. But the box is not going with the pull of the worker, it's going with the x component. The x component is what's making the acceleration along the horizontal wood floor. So that is the forward force. Not 200, but Fx. Minus force of friction over mass. In other words, the numbers are the 173 let's do a little jailbreak here for our calculations. Minus 87.6 newtons, all over the mass of 40 kilograms. All we have to do is now punch that in on a calculator, and we get 2.1 meters per second squared. Okay. So, if you need a little moment, I'll pause here, give you a chance to catch up. Okay, so remember I said this back when we started with Newton's second law. I said the concept is easy. More force, more acceleration, more mass, less acceleration. The hard part is the application. Look at all we had to do. We had to do all this thinking, and then the normal force gets smaller, and then this, and then we had to do all this calculating, and finally we get to A equals F net over M. And then we had to use the X component minus friction. And then, so this is like the easy part when you get to A equals F net over M. The thoughts and the pre-calculations, that's the hard part of the problem. And that's just dragging a box along a wood floor up at an angle. Imagine an airplane taking off with wind and tires and all this stuff and people in different parts of the plane, right? Real life, extremely complicated, okay? So that's example 3. And as I said, that's not what I want you to emphasize. It's in your notes. Good, if you have time and energy, study it. But here is the key of what I want you to take away today. Okay. So here's our summary. So if you have a force diagram that looks like this, applied force and friction less. Okay, so draw that shorter. And of course, we've got our normal force and gravity, which are balanced out. So I draw these best of my ability to equal length. Then, well, first, before I do that, let's just draw the other situation that we studied today. We had the same in the vertical, gravity and normal force. So gravity down, matched by normal force. But the key difference is, in this other scenario that we studied, this and the applied force and the friction were equal. So equal, we'll put these little marks down like this to show that they're equal. This scenario, more force in the forward direction, this is the object speeding up. Whether it's a box or a rock or whatever, or a kid in a sled and you're pulling them, right? More forward force, speeding up. We have a net force. When these forces are balanced, one possibility is this object is at rest. Like when I'm pulling on a kid and then we hit like maybe a piece of asphalt and they stop because there's no snow there, and then I pull and I can't get them moving, right? So I'm pulling and then the friction's matching. Okay, I'm at rest, I'm stuck. But the other possibility is it's moving at constant velocity. When you see those words, constant velocity, that should be a trigger about forces balancing because of acceleration 0. So these, example 1 and 2, those are the ones I really want you to know and be ready to apply. And then don't forget about kinematic graphs, constant velocity displacement, accelerating displacement with a curve, velocity graph like this or like that, depending on acceleration or constant velocity. A equals F net over M, forward, friction, normal force, gravity, and that's it. Okay, so I hope you enjoyed the video. I'll see you in the next one.